Yeah, thank you, Francis, dear colleagues. It's wonderful to be here. Thank you for the invitation and having me here in Nottingham, meeting some of my old collaborators here right in the audience. I would like to, before I actually talk on eccentric exercise, I was wondering whether, with regard to the previous talk, it wouldn't be interesting to have fiber type specific data, not only global data, because I think that could be one of the differences in high intensity sprint type training. So let's now move over to eccentric exercise. And as you know, with our muscles, we usually think about doing positive work, mainly contraction, shortening of muscle fibers, which provides then the concentric muscle action and provides positive work or acceleration. This is how we usually think about muscles. And we forget that over a lifetime, we more or less have to do as much eccentric work in terms of when we neglect friction. Basically, we would have to do exactly the same amount of eccentric work walking around, because otherwise we would end up on a different altitude dying than when we were born. Negative work is eccentric muscle contraction, is activating the muscle while it is lengthening and resisting, thus, elongation of the muscle. It's also deceleration. We can explain muscle contraction, and we have been able to explain it very nicely for quite a while, since the mid-50s. We can explain it by the activity of the actin-myosin system. However, it is currently unclear how the muscle actually performs eccentric contraction. We do not know for certain what the mechanism is which allows the muscle to resist elongation in a convenient manner. It is titin which has been named the third filament, which seems to be responsible for elastic property and is also implicated in lengthening behavior of muscle tissue. Actually, there are people who believe that it is calcium-controlled titin elongation or titin actin binding, which is controlling lengthening contraction. But as I said, the book is still open. We use eccentric contraction when we work downhill, negative work, elongation, resisting elongation, as I explained it. But we also use eccentric contractions for elastic storage of energy, i.e. we contract muscles and let then the tendons do the work. So actually, this is a second way of using it. And there is a third way still that may be noted here, and that is that you use eccentric contraction when using biarticulate muscles to transfer torque from the more close to the large muscle groups that are close to the body to the periphery. So eccentric exercise is also used in transfer of torque to the periphery of the limbs. When we look at the physiology has been well explained for the concentric part, and it's actually A.V. Hill who was one of the first to note these characteristics, that is, that as contraction speed increases, torque decreases, so that at the maximum shortening velocity, the torque that the muscle can produce is actually zero. This doesn't happen in eccentric contraction, where first there is an increase of torque, and then the torque stays the same at increasing shortening velocities. That is generally accepted. And this is as we see it in single fiber experiment. When we look at in situ muscles, this doesn't happen exactly that way because, of course, there is a limb attached to the muscle, and therefore here the torque will not go to zero, nor are we able to reach maximum shortening velocities of our muscle fibers. But the general shape of the curve, namely the decrease with increasing shortening velocities and the increase with isometric contraction, and then the constant torque production during increasing speed eccentric contraction remains the same. What is often overlooked in this situation is what power does, and power is angular velocity times torque. So of course, as long as angular velocity is zero, power will be zero. Power with concentric contractions then increases, has a maximum, and starts to decrease again as torque drops with increasing velocities. This is not the case for the eccentric part of the curve, where negative power, braking power, increases with speed, but then continues to increase without a limit, because torque stays up and negative angular velocity continues to increase. So basically, there is no limit to the amount of negative work that the muscle can do. And it is therefore evident that this is calling for disaster. And we all know that acute eccentric exercise can lead to delayed onset muscle soreness, which is structurally evident as disorganization of myofibrils in skeletal muscle fibers, or even, as we have shown quite a while ago, can lead to microlesions in muscle tissue that then take several weeks or even months to repair. Now, back to some basics of eccentric muscle contraction and why we don't know what is actually happening. And the critical experiment, one of the critical experiments is shown here. As you all know, there is only a short range of sarcomere distances over which maximal torque can be produced. This is between 2 and 2.2 microns of sarcomere length, because here we have optimal myosin-actin overlap. If we go to shorter sarcomere lengths, tension drops because actin and myosin get in each other's way, and eventually the myosin hits the C-line, and we actually have no more possible for torque production. It's easier on the descending limb here, where sarcomeres get longer as we pull out the actin filament. So the number of cross bridges that can form during the contraction decreases, and we have a linear decrease of the potential for force production based on this actin-myosin interactions. Now, if we look at the other slide, you can see that we have here a sarcomere length of 3.4. That means we are about here. And as a consequence, with 3.4, you can only produce a relatively small torque. And this has been done on single fiber and even on single sarcomeres. When we now go to 2.4, of course, this is 2.4. Here we can produce more. More tension. And when we now take this experiment and then go with a muscle stretch to 2.4, stretch it to 3.4 microns, then you see what happens is that the tension doesn't drop, but the tension rises and then stays up, and it stays up higher than it was here. And this is called force enhancement. And the problem with this situation is that it's very difficult to envisage how now at the sarcomere length of 3.4, the muscle fibers can actually produce more tension than they could when they were in the elongated position. So there is a history of torque production in muscle depending on whether you get to a sarcomere length by lengthening or whether you just went there in a normal contraction. And it is claimed that this basically rules out the actin-myosin system, also that, as I said, there are other options which would like us to have this explained in different ways. I would not like to go into these options. What is better known than the basic physiological mechanism is that, and that has been researched much by Biggle and Ritchie, is that we are all aware of the fact that we use much less, it's about 4 times less energy to produce eccentric than concentric work. So the work rate between the same power output when you do concentric to eccentric work is about 4-fold. And we also know that the EMG level that you use in eccentric work is only about half that much that you use for the same concentric power output, which, by the way, means that it is more difficult to control, coordinate eccentric contractions. Now, when I go into the application, strength training has been done with eccentric overload. This is a possibility to do eccentric exercise, which would mean that during a normal session in a strength training where you concentrically contract your muscle and lift the load and then you lower the load, of course the eccentric phase you have about 20 to 30% less load with regard to the maximal load you could take in the eccentric phase. And this can be compensated by eccentric overload. So add weight during the eccentric phase or help lifting during the concentric phase. You can use a pointer. You can use 2-leg versus 1-leg exercise. You can use one of various yo-yo devices initially conceived by Per Tesch and used in space programs, or now available also classical strength training machines which swivel the weights during the eccentric contraction to the vertical, whereas it's on this incline that lowers the load during the concentric exercise, so that during concentric and eccentric phase of strength training, you have the relative same amount of load on the muscle tissue. I don't want to talk about these modes of exercise in the rest of my talk, but I would like to talk about moderate load eccentric exercise, which is a continuous application that you have a motor-driven treadmill, use a controller program, and then you actually resist these motion, and you can give the subject a target load here, for instance, 100 watts, and then you can see here, what you see here actually is the anchor current of the machine. It's that allows you to see what you're doing, and then you can target your load to a specific intensity. This is available also as bicycles that you can resist. They have a motor here in the back, but when you just sit on the bike, there's about 500 watts, the maximum that you can use as a load, because otherwise you're lifted out of the saddle. So we use this mode of exercise in a continuous program running that for usually 20 minutes or bouts of 4 times 5 minutes. And I can say that when you use this exercise mode, eccentric exercise on an untrained person, then 100 watts, a single bout of 10 minutes of 100 watts leads you to a delayed onset muscle soreness that makes you walk backward the stairs on the next 2 or 3 days. We have used this load, and now what this means is you cannot start with high loads. You have to start with very low loads with eccentric exercise. And what we have done here is have young subjects train at the same VO2 max, either with concentric loads, 120 watts, or 490 watts with eccentric loads. And you can see here when you slowly ramp up the intensity of the exercise, then there is practically no muscle soreness. Sometimes you have it when you step up the intensity. What we found under these conditions is that eccentric exercise leads to an increase of isometric strength and also leads to an increase in muscle fiber size as evidenced by biopsies. What we've also shown using these college-level basketball players is that the eccentric load, the same time of concentric concentric training, which consisted in weightlifting, versus eccentric biking on the machine that I showed previously, showed that there was an increase in jumping performance, quite considerable increase in jumping performance, which may be to the fact that we could show that the muscle stiffness was increased as evidenced by an increase in the hopping frequency, spontaneous hopping frequencies of the subjects, which enabled them to reduce the contact time, efficiently reduce the contact time, and transfer more elastic energy into the next jump. Of course, that is my favorite sport, and what you do here is this guy is one of the top alpine skiers we have in Switzerland. We have fixed accelerometers on their chest, and what they're doing in giant slalom turns is actually they resist 3G loads. We recorded 3G loads, which means that he dynamically, eccentrically balances about 250 kilograms on his right leg here, turning at 80 kilometers an hour on an icy slope. So this is quite a feat, not only in terms of coordination, but also in terms of muscle performance. The Swiss ski team therefore uses an eccentric machine that is considerably stronger, and we have people train at performance negative workloads up to 1600 watts. And you can see that we not only have them sitting, but we also have them standing. Here the heart rates continue to be low, as we would expect, but as soon as you have them standing, you have so much muscle activated for the coordination of the movement that they can only do relatively short bouts of 3 to 4 minutes of maximal eccentric exercise, and their heart rates just explode. With alpine skiers, with junior alpine skiers, we could also show that jump performance as well in the squat as in the counter movement jump increased when comparing groups that did a conventional concentric as compared to groups that did an eccentric training over an intervention period of 6 weeks. An interesting aspect is that eccentric contractions on the bike are difficult to control. And the machine allows us, of course, to measure coordination. I don't know exactly what this means in this context, but you can measure the area under the curve, and the coordination is better when the area of the curve is low because you can achieve the target load more smoothly. And we have done that for alpine skiers, and only for slalom skiers we found that the initial capacity to coordinate at their first training, and it's only at the first training, where we loaded them with 500 watts. You can do that with skiers because they're doing eccentric work. You can show that there was a correlation between the FIS points, their FIS standings in slalom, and their capacity to coordinate, to have an as low as possible area under the curve when doing the first eccentric performance. We have used eccentric exercise with cardiac patients from an ambulatory cardiac rehab program. We did a prospective randomized intervention with training 30 minutes, 3 times a week for 8 weeks. And we did a right heart catheter after 5 weeks, because obviously what you would like to do is have people train at the low cardiovascular load, but at the high mechanical load for the muscle tissue. So what we saw in this group of people, where we used the right heart catheter because our cardiologist felt that the eccentric exercise at these high loads that we are using were not healthy for the cardiac patients. And here you see exactly what we did, as we did in the untrained group, not with VO2 max, but with heart rate. We controlled the heart rate, and these 2 groups, the concentric group, worked at the same. Here, these are the bars. They worked at the same heart rate than the eccentric group, but this was the power that they resisted. This is negative work. Positive work done at the same heart rate, and you can see that was at 75% of their maximal heart rate. Again, you can see the difference between eccentric and concentric work. It's almost 4-fold. You can also see that we couldn't increase the workload anymore after 5 weeks with the eccentric training group, not because this wouldn't have been possible, but because the ethical committee insisted that we are not allowed to increase eccentric workload after 5 weeks anymore. What we could do with the right heart catheter was that we could show that whether you work concentrically at the 100 watt or eccentrically at 360 watt, you have the same pulmonary arterial pressures, and you have the same wedge pressures. And we have done quite a number of additional measurements done with ultrasound. And we therefore can say that there is not a real difference between these 2 modes. What we saw as a difference was that there was an increase in strength during concentric exercise, not during eccentric exercise for the work done with the eccentric group. We have also used this training regime in sarcopenia, again, because it would be nice to be able to have high mechanical loads on muscle tissue with low cardiovascular involvement. We had about 80 patients with aged 80 and over, with cognitive training, classical resistance training, and eccentric training. And we of course could see that everybody increased except the cognitive group, which is not shown in terms of the loads that they could perform. We could also see that there was a significant increase of strength with this protocol, again, due to the ethical committee. And we could see that we had an increase in muscle mass with the training groups, but not with the control groups. And we also saw a decrease in fat content, most pronounced with the eccentric training group. What an interesting feature here is that the coordination was the only feature that when we controlled these people a year after the training intervention, that a year later the eccentric coordination group could still coordinate better than all the other groups. So that was a remaining effect, a learning effect that persisted, and may be important related to falls in that age group. What I have to say is that when we looked at gene expression from the biopsy study, then we had an increase in gene expression for genes related to remodeling, but the decrease in genes related to metabolism and mitochondria, so there is a negative side to eccentric exercise too. I leave that because we don't have the final results of the fMRI study, but we believe it is the control, the central control is different in concentric and eccentric exercise. For instance, evidenced by the fact that nobody is able to coordinate more than 80, 90 RPMs eccentrically, while it's easy to go to 150 with concentric exercise. So finally, summary, immediate effects of a single bout is a reduction of performance, muscle damage, increase of CK and other marker of muscle damage. With moderate load eccentric exercise, 3 times 20 minutes per week, we found an increase in muscle strength and cross-sectional area, similar to that seen in classical strength training, decrease of fat content, local and in the whole body, an increase in eccentric coordination, an increase of the stiffness of the muscle tendon unit, and exercise with low metabolic requirements for high mechanical loads is, at least with regard to the cardiovascular variables we measured, seems to be safe. So you can do a strength type training with low joint loads. But on the other hand, we see a decrease of oxidative capacity of trained muscles, and we have seen that in the 3 studies that we have carried out with biopsies. Thank you very much for your attention.